Welcome to the third and final lecture in Unit 5, the Global Ocean. This chapter is, this lecture will cover Chapter 15, the Dynamic Ocean. In this lecture, I'll be discussing the surface and deep water circulation in the ocean system, as well as the nearshore processes, wave formation, wave structure, wave mechanics, and shoreline structures that are at the interface between humans and the ocean, namely beaches and coastlines. And then finally we'll be talking a little bit about tides. So the first section, we're going to be looking at large scale ocean processes, large scale ocean circulation and deep water circulation. Ocean currents move water, or scientists view them as water masses, not discrete blocks of water, but water tends to move in kind of large masses throughout the globe. Surface currents develop from friction between the ocean and the wind that blows across the surface. That is, in the next unit, Unit 6, we'll be talking a lot about atmospheric circulation. But really what drives surface ocean circulation is atmospheric circulation. That is wind. Wind moves across the surface of the ocean, and the frictional interface between the two causes an interaction. And each affects the other. The way that wind or atmospheric circulation affects ocean circulation is that it causes surface ripples and waves and currents to move. Deep currents, on the other hand, are driven not as much by atmospheric circulation, rather they're driven by density differences, inertia, upwelling and downwelling forces, which upwelling and downwelling forces do have a component that's driven by atmospheric circulation. So it's not fair to say that deep currents are not completely decoupled or non-interacting with the atmosphere. They are. Surface circulation in the ocean system takes place in what are known as gyres, or geostrophic gyres. Gyres are slow, generally circular surface currents. And you can see on the map below there are several different kind of loops or circulation patterns in the world ocean. In the North Atlantic, you have what's called the North Atlantic gyre, and you see water circulating in this kind of clockwise rotation. In the southern hemisphere, in the southern Atlantic, you see a counterclockwise rotation of a gyre. In the equatorial and southern Pacific, you see another counterclockwise rotation. In the northern Pacific, clockwise rotation. In the Indian Ocean, which is in the southern hemisphere, you see a counterclockwise rotation. These gyres there are 5 main gyres in the world. We've just reviewed those: the North and South Pacific, North, South Atlantic, and the Indian. These gyres do interact. So I'm not saying that, say for instance, the South Atlantic gyre, all water in the South Atlantic stays in the South Atlantic for its entire lifetime. Some water does get transported or exported out into the Antarctic circumpolar current, which can get entrained in the Indian Ocean, so on and so forth. But for the most part, surface currents in general do move within ocean basins. Now, the reason these gyres exist have several reasons. There's several kind of controlling forces. Atmospheric circulation, that is wind, primarily drives surface currents, especially in the equatorial regions where winds generally move east to west, that is east to west. And you can see this pattern of air movement in the equatorial band definitely moving to the left. Now, when wind blows, when wind blows across the surface of water, there's an interesting phenomenon that's called Ekman circulation or Ekman transport, and that is that water molecules tend to move at a slight, right angle or slightly offset to the direction of wind blowing. And that's due to the way the water particles interact with each other at depth. It's beyond the scope of this course, but nonetheless, as the wind is blowing from, in this diagram, right to left, water is actually moving a little bit kind of bottom right to upper left. Now, other forces that affect circulation patterns are gravity, that as water tends to pile up in the center of these gyres, it tends to flow downward and outward, and as it does, it keeps that circulation moving. The third major force is something called the Coriolis force, which is best if you look up. If you were to really be curious about the Coriolis force, you would look up online, just Google search like Coriolis force video or something like that, and it would show you kind of in animation terms what happens with the Coriolis force or why it works. But what it essentially is is a particle in motion, water, a missile, a tennis ball, an airplane, tends to follow a pathway that curves to the right if it is in the northern hemisphere. And if it's in the southern hemisphere, it tends to curve to the left. So the Coriolis force is basically due to the rotation of the Earth as it interacts with particles that are moving on the surface of the Earth or above the surface of the Earth. And that is the primary reason why, in the case of the northern hemisphere gyres, they move clockwise. They are bending, always deflecting toward the right. They're set up by the equatorial bands of wind that blow them right to left or east to west, and they bend or deflect to the right. Same in the equatorial northern Pacific. And then in the southern hemisphere, on the other hand, we have the bending to the left. Now, the other last controlling force for gyre formation, or last influential aspect of the Earth system that interacts with the gyre and causes it to form in the way they do, is ocean basin geometry. Now, water would tend to, for example, in the northern hemisphere Atlantic basin, water would tend to be moving and keep wanting to move this way up into where the upper northwest, Pacific Northwest is. But there's a continent in the way, so it actually deflects and curves around. So ocean basin geometry is the fourth major factor in determining how gyres form, where they form, and their characteristics and dynamics. Now, each gyre system has four major currents. There are boundary currents, which occur on the adjacent to continents. Boundary currents are usually the north-south or south-to-north traveling currents. So in the case of the Gulf Stream in the North Atlantic Gyre, the Gulf Stream is a boundary current. It's called a western boundary current. The eastern boundary current would be over here, the Canary Current. In the South Atlantic Gyre, the western boundary current is the Brazil Current. It's moving down. And the eastern boundary current is the Benguela Current. Then there are transverse currents, and transverse currents move left to right or across the globe in latitudinal bands. The South Equatorial Current or undercurrent, the West Wind Drift, so on and so forth. This slide should be familiar. We saw it in the last lecture in chapter 14, talking about the high heat capacity of water and how surface ocean circulation and deep water circulation have important ramifications in terms of the Earth's climate. Remember, surface currents will transport a lot of heat from the tropics. They'll export heat from the tropics toward the poles or the high latitude areas. Influence of cold currents is most pronounced in the tropics or during the summer months of the middle latitudes. That's when these currents are bringing, they're not bringing coolness to the tropics. What they're doing is they're bringing water that has the capacity to soak up heat to those regions. Florida is a great example of how water's heat capacity can moderate and really influence the climate. If you were to, in the middle of July, say, take a drive up to, say, South Carolina, near the Georgia border, or northeast Georgia, or northern Alabama, southern Kentucky, southern Tennessee, anywhere in the eastern seaboard where we get a lot of Gulf moisture due to atmospheric circulation patterns, it is hot as the hinges up there and very, very humid. 100-degree days, 98-degree days, pretty regular. Whereas on the Florida Peninsula, and especially along the Florida coast, if you live in Pinellas County or Hillsborough County, or anywhere on the Florida coast, you rarely see temperatures above 96, 95, 94. Even when northern parts of the United States or the Midwestern and southern areas of the United States are enveloped in heat waves, the Florida Peninsula, which is surrounded by this basically natural air conditioner, this body, this phenomenon that can soak up heat, keeps Florida's climate quite moderate, especially considering where we are latitudinally. Now, upwelling is of importance when it comes to nutrient levels in the ocean. Remember, upwelling, if you think back to the last lecture, we showed the picture of, or I showed the picture of primary productivity around the world, or chlorophyll concentration as a proxy for biological activity or the vitality of a system. Remember, the coastal regions had tremendous amounts of chlorophyll production in many cases, due to nutrient supplies from the land. But upwelling is another way in which those deep, cool, nutrient-laden waters come to the surface. And the way that happens is illustrated here. For example, in the African continent, you have the Benguela Current, or Benguela Current, traveling northern from south to north, and the winds. Remember, the winds are traveling also south to north, but due to Ekman transport, the current is moving slightly offset to that, at a slight left offset from that primary wind direction. What that does is it moves surface current away from the continental mass. It's moving surface waters from the shoreline away and out. Well, when surface waters are moving away from a landmass, something has to come in and replace them. And what happens here is that deeper water that exists below the surface is being brought to the surface as the surface current moves away, creating a vacuum of sorts. And you can see these chlorophyll concentrations off the coast of Africa are very, very, very high due to upwelling of deep nutrient-rich waters caused by surface currents traveling in a norther or northwesterly direction. Now, the deep ocean circulation that we touched lightly on in the last chapter is illustrated here. Deep ocean circulation is known as the thermohaline circulation system. Thermo meaning heat, haline meaning salt. Remember, it's a density-driven circulation, and what drives seawater density, or what controls seawater density, that is the temperature of the water as well as the salinity of the water. This thermohaline circulation, or the THC, another name for it is the meridional overturning circulation, or MOC. Not really important to know those particular details of the names. You just want to understand what it is. And what is thermohaline circulation? Well, it's driven by density differences in water masses, salinity and temperature. Water masses that are heavier, that is denser, will tend to sink relative to water masses that are less dense, warmer or less saline. Most water involved in deep ocean circulation begins in the high latitudes at the surface, and because it is cool when it gets to the high latitudes there or down in here, when it gets to the high latitudes, and because air temperature is so cold it loses its heat and becomes cooler, it also becomes denser. Now, there is some degree of precipitation-induced freshening, or ice cap melting freshening, which causes the salinity to drop and therefore the density to increase. But for the most part, when water gets to high latitudes, it gets colder and denser and tends to sink. Now, the conveyor belt model, a lot of scientists and media people tend to show this picture of the ocean as this one big circulation system that seems to look like a conveyor belt, where water starts in the Gulf of Mexico, or wherever you start, it eventually gets around, but starts in the Gulf of Mexico, moves out to the North Atlantic, sinks down deep, travels through the South Atlantic, through the Antarctic Circumpolar Current, up through the Pacific Ocean, where it rises in the temperate Pacific, rises up, travels back through the Indian Ocean, back through the South Pacific and into the Gulf of Mexico, actually drips into the Gulf of Mexico and comes out here. So the thermohaline circulation, or the conveyor belt model, kind of illustrates how the different oceans around the globe interact, and how they are really connected to each other. It also impacts, or it also illustrates how heat is transported around the globe, and the general pattern of circulation. Now, moving from really, really large scale stuff to smaller scale phenomenon, we're going to move from large ocean circulation patterns to more wave formation processes and the interaction of the ocean with the land, which occurs along coastlines. Now, the land-sea boundary is an interface. We talked about interfaces before. One of the big ones was soil, where you have mineral, you have the geosphere interacting with the hydrosphere and the atmosphere. Well, the land-sea boundary is an interface where the hydrosphere is interacting with the geosphere. That is, the ocean, part of the water cycle, is interacting with continental crust. Now, the land-sea boundary has several components. When you're at the beach, this is just a kind of a geologic framework for understanding shoreline or nearshore processes. It's a nomenclature or a vocabulary that allows us to be precise in what we're describing. Offshore is basically where wave base doesn't really interact. Waves don't interact with the basin. But the nearshore is where the altitude or the depth, basically the bathymetry, is rising. Waves become more important in processes underlying or on the seabed. The shoreline is the contact point between land and sea that is variable as tides move in and out. The shore is the area between the lowest tidal level and the highest areas affected by storm waves or tidal forces. So shoreline starting there, shore starting there, all the way up to the what is basically the coastline, the seaward edge of the coast, where beyond which waves and water do not interact. You have marine influenced systems like dunes forming, and it seems to be related to the water, but it's actually not ever in contact with surface waters. And the beach is the accumulation of sediment along the landward margin of the ocean. Now, waves are the really kind of fascinating part of the interface system for a lot of people. Now, there are scientists who study strictly shoreline processes and beach processes. They're more interested in the grains of sand and the structures, how the structures ebb and flow, how the geomorphology changes due to different kinetics and dynamics of marine systems. But waves, from a purely physical standpoint, are really interesting things. Waves are really energy traveling along the interface between the ocean and the atmosphere. If you really want to define it, they are energy. They derive their energy and motion from the wind. That is, the wind and the superficial, or the drag that wind puts on the water surface as it blows across, is what generates waves. They start off really, really small, and they eventually can reach fairly sizable sizes. Sizable dimensions, I guess, would be a better way of saying that. The main parts of a wave are the crest, which is the top, and the trough, which is the base. And the difference between the crest and the trough is the wave height. The distance from one crest to another crest is called the wave length. The wave period is the time interval for one full wave to pass a fixed position. So if you said the period was 10 seconds, every 10 seconds a new wave would come by you. If a period of a wave was 50 seconds, it would be every 50 seconds a new wave, a single new wave would come by. If it was 1/8 or 1 hertz, a hertz is a fraction of a second. If it was 8 hertz, which is the same as 1/8 of a second, it would mean that every 1/8 of a second, or 8 times per second, a wave would travel by you. You can imagine the size of the wave is related to the period, and it is. If you have waves coming by 8 times a second, they're probably going to be really, really small waves. They can be kind of what you would consider ripples or riffles on the surface. Whereas if you had a wave coming by every 10 seconds, you can imagine if you're ever been to the beach, that every 10 seconds a wave is going to be pretty sizable. And that's true. Now, wave height, length, and period depend on the wind speed, the length of time the wind blows, and the fetch. And the fetch is basically the distance across which the wind can blow unfettered and develop or build waves. Now, wind speed seems pretty intuitive. The faster the wind blows, the larger waves will get. The length of time is also somewhat intuitive, whereas the longer wind is blowing across a body of water, the more phased and the more systematic a wave system can be. And the fetch is the distance at which the wind blows across. Now, wave motion in itself is relatively circular. Energy is moving forward, but what is happening to that energy, or the way that energy is propagating, is that particles of water are impacting each other in a circular motion. They're kind of rolling by each other. If you were a boat, you can see this kind of circular motion as a wave would transmit by. As the boat rides up on the crest, it comes back, as illustrated by here, and kind of comes back into a circle of motion. That's what, or that is the physical dimension, the physical aspect of wave propagation. Waves have predictable patterns, especially when they approach the shore. The depth of a wave, or the depth that a wave will interact, that energy is actually propagating forward, is generally thought to be about 1/2 of its wavelength. So if a wave is 10 meter, has a 10 meter wavelength, that is, there's 10 meters between the crest of a wave here and a crest of a wave here, that wavelength is 10 meters, the depth that wave is interacting is only about 5 meters. It's half the wavelength. So as waves approach shore, the depth of the sea surface or the depth of the ocean floor decreases. That makes sense. The wavelength between waves decrease. The wave height increases, and friction increases the wave crest. The friction increases the base, and the wave crest actually moves faster than the wave breaks, which causes the wave to break, lose kind of integrity, lose its structure, and fall over. So you can see that as the depth of that interaction gets closer to the seafloor, this is a 10 meter, we'll call it a 10 meter wavelength wave, 10 meters from there to there. The wave base is therefore 5 meters. When that shoreline, or when that ocean bottom gets to be less than 5 meters, that wave all of a sudden the energy in that wave starts to impact or frictionally interact with the ocean floor and causes the base of that wave to slow down. You've got friction happening. The top of the wave, which is being driven by wind and inertia, is still going the original speed, and it tends to kind of fall over. Now, the ways that waves interact with the shore and at the shoreline interface, or the coastal interface with the geosphere, are numerous. Wave erosion is the main force that determines the macro and micro scale geomorphology of any region. That is, macro scale meaning large shoreline structures, coastal bodies, and then also the micro scale coastal geomorphology. That is, the type of sediments, the type of deposits that are extant on a beach face, or the type of erosion that's occurring, or the depth of the shore face and the angle at which that declines into the deeper ocean. Now, wave impact and pressure will break down rock material and it, in general, supplies sand to beaches. But it also causes abrasion. That is the kind of smoothing and grinding action of water with rock fragments. That can cause a lot of erosional processes as well. Wave refraction is relatively important. It causes generally irregular shorelines to become flatter and more regular with time, and that's because the refraction of waves, which is a general physical process of meaning that refraction is when a wave is moving and there's a change of direction. When its energy and momentum change, the direction and the rate of motion of the wave will also change. It's basically the bending of a wave. Now, in this example, we see a series of somewhat parallel waves approaching a shore, and when they hit that headland, you can see on the side of the headland, those waves actually bend and tend to focus their energy inland onto that headland. A lot of the wave energy is redistributed toward the point at which it contacts first, which tends to, over time, flatten that section of headland and would make a more of a regular coast. This is a photographic example of seeing waves coming in off of a breakwater or a kind of an inlet area. And you can see those waves curve around the shore and actually end up directing themselves against the shore in a direction that's normal to the main direction of wave propagation in this environment. Longshore transport is another really interesting beach process. And if you go to the beach a lot, you probably know exactly what I'm talking about when I say when you head down into the water through the first row of breakers, a lot of times you'll get into kind of a deeper zone, which then can, if you keep walking out or keep swimming out, will level off and there'll be a bar or two further out. That kind of trench or trough right off of the shore face oftentimes has water moving left or right, depending on the day, with some force. A lot of times if you're in Pinellas County and you've ever been to Paso Grill or St. Pete Beach, and you go off 10 meters off of the shore face and you just sit there, your body will kind of drift down along shore, either north or south, depending on the day. But that's what's called longshore current, and that's caused by waves hitting the beach face not head on. So if waves hit the beach face exactly straight on, then they tend to bounce back off and wash, retract backwards straight out. But if they hit at an angle, that is, if the wind direction is not blowing exactly on shore, if the waves are coming in at an angle, what they tend to do is go hit an angle in a zigzag pattern, and so you get this wave washing up, wave washing back, wave washing up, wave washing back, in this zigzag that ends up transporting material in this picture from left to right. It can go the other way if the waves were coming in at the other way. Now, the longshore current is that current in the surf zone that flows parallel to shore, and it actually moves a substantial amount of sediment along the shore, not just pushing it up and down like beach drift does. Some other features that you see in coastal environments, shoreline environments that are depositional in nature are spits, which are ridges of sand extending from the land into the mouth of an adjacent bay. Often one end hooks landward. This is a famous one, the Provincetown off of Cape Cod, this spit that hooks back around. Baymouth bar, it's a sandbar that completely crosses a bay. This is a good example. The tidal delta is an erosional feature that we'll see that's caused oftentimes. They coexist with Baymouth bars, but that's that. And a tombolo, which is a ridge of sand that connects an island to the mainland. Oftentimes you'll see those during low tide stands, especially in the northeast United States and upper Pacific Northwest. Barrier islands are depositional features that are much larger in scope than the spits and the Baymouth bars and tombolos of the previous slide. Barrier islands mainly occur on passive margins where there's lots of sedimentation, lots of deposition, and fairly little deformation processes and uplifting processes. They run parallel to the coast. If you live on the Gulf Coast of Florida and you're taking this course, then, or if you live in Pinellas County, we're fringed with a series of barrier islands. St. Pete Beach, Madeira Beach, Treasure Island, those are all barrier island formations. They're really dynamic bodies, and a lot of development occurs on barrier islands in the United States. These are inherently geologically unstable structures. They're moving all the time, and really are not the best places to build in a lot of ways, but then again they're usually quite beautiful, and people will flock to them. So it's kind of a tricky situation, balancing the geologic nature of barrier islands with the desire of human beings to build structures and roads and fun centers and things like that, and tiki bars on them. Some erosional features that you find along shorelines are illustrated here. We have some wave cut cliff and platforms, marine terraces, basically as uplifted areas, especially that are areas that are tectonically active, where you have crustal deformation and uplift, which can occur in kind of fits and starts. If you uplift an area, then the wave action that is in that area has some time to really do its erosional work, and then it uplifts again. The more erosion, uplift again, more erosion. You get these kind of terraced structures where you have a flat marine eroded terrace, then a cliff, then another marine terrace. Sea arches and sea stacks are other erosional features. Sea arches are things that often occur where there's a decent amount of tectonic uplift again, where you have vertical structures, vertical rock formations. They let's see. Oh, this over here, shoreline erosion is influenced by local factors. It really is. Shoreline deposition is influenced. Deposition and erosion are influenced by the local factors. So, sediment-laden rivers, if there's a large source of sediment coming in, oftentimes you don't have as much erosional features showing up because the erosional forces are kind of already at capacity. Now, how do humans respond? How do we deal with these natural erosional problems that occur along coasts? There's two ways. One is called hard stabilization, and the other is alternatives to hard stabilization. So hard stabilization is building structures to stop, or at least to try to slow down, coastal erosion processes. Groins are barriers built at a right angle to the beach. They're designed to trap sand. You can see down here on this bottom picture, these things sticking out in the water are actually called groins. Groins have an interesting, what happens is they defend against the longshore current, as this longshore current that is moving either bottom to top or top to bottom. In this picture it's really impossible to tell, but it doesn't really matter. That longshore current is moving along, it's moving a lot of sediment and eroding a lot of sediment from the edge. When people build these basically walls that stick out, it stops that longshore current from digging in and eroding out. What it actually does is it builds up sediment. It actually causes the longshore current to drop its sediment upstream or upflow from those groins. What it also does is tends to allow that longshore current to pick up more sediment from downstream of those groins. And so when you have a lot of groins, they typically tend to propagate in the direction of the longshore current. As somebody builds it, the next guy living down the beach from him, who all of a sudden now has a lot of erosion occurring on his beach, builds that, and the person who lives next door to that person then has to build it. So they're kind of a sequential thing. Breakwaters are built offshore and parallel to the coast. They protect boats and land from breaking waves. They tend to reduce the strength of breaking waves. And seawalls are literally walls that are built along the shore to protect the coast against the force of breaking waves and try to mitigate or eliminate erosion. But oftentimes those structures are not effective. The wave systems are working 24/7. 365 days a year, and human-made jetties and seawalls are oftentimes insufficient over long periods of time. So alternatives to hard stabilization have been adopted in many locales. Beach nourishment, which is adding sand to the beach system, is an important alternative that is used in a lot of places. You can see this is a before picture down here of Miami Beach, and here's an after picture. I flipped them around. I should have had the after on the bottom, but you can see how the beach is miraculously back in place. This is not a shot of different tides. This is all that sand has been brought back into place and dumped there. Now, beach nourishment is also really difficult to do well because every beach has its kind of natural state of grain size, which is based on the energy dynamics of the wave face and the wave system. And a lot of times you just bring in some random sand from somewhere else. It doesn't have the kind of the right mix that can stick around in the conditions that exist. The Atlantic and Gulf coasts have a number of erosional problems, and that's because development mostly occurs on barrier islands and low-lying beach faces. They face the open ocean, and they receive the full brunt of storms that pass by. Development has really exceeded or been far ahead of our understanding of barrier island dynamics, and in a way it's too late. It's not like we can tell all the people that live in these really, really beautiful condos and houses along our beaches along the East Coast that they have to move. But if in hindsight, if we could do it all over again, things might have been done differently, I imagine. The Pacific coast is a little bit different. They're characterized by relatively narrow beaches because it's an active tectonic continental margin. They're relatively narrow beaches backed by steep cliffs and mountain ranges. The major problem is the narrowing of beaches, and since there's so much competition for water resources in the western United States, dams or rivers are starved for sediment because of the use of dams and reservoirs. So therefore there's lots of rapid erosion occurring along beaches, especially near sediment or sediment-starved river systems. Shorelines can be classified in a number of ways. Classification can be based on changes with respect to sea level. Emergent coasts are generally near areas of uplift of underlying and adjacent land, or areas where sea level has been dropped or sea level has been declining. Emergent coast features are typically wave-cut cliffs and marine terraces. So emergent coastlines are, you can imagine, they're more active tectonic margin type of thing in the western United States is where you'd find most emergent coasts. Now, submergent coasts are in passive continental margins, where land adjacent to the sea is subsiding or sea level is rising. Submergent coast features are highly irregular shoreline versus sharp kind of cliff and tectonically simple structures, and estuaries, which are drowned river mouths. One of the most famous estuaries or most productive estuaries in the United States at some points in the time, or United States history, has been the Chesapeake Bay estuary system. This bay system actually drains the Susquehanna River, which comes in right through there. The Susquehanna River rises in Cooperstown, New York, and travels all the way down to I don't remember exactly what that town is, but when sea level was much lower, this was all part of the Susquehanna River Valley. Now it's a large estuary. Estuaries are environments where freshwater and saltwater mix. They're They're highly diverse, highly nutrient rich, incredible sources of productivity and biological activity. Now, the last part of this chapter, moving from shoreline processes, we're going back to kind of large scale, and it's tides. I say large scale because tides are really driven by astronomical forcing. So the reason for tides has really nothing to do with Earth processes. They're really all based on the changes in elevation of the ocean surface that are caused by gravitational attraction or gravitational forces exerted by the Earth. Exerted by the moon and the sun on the Earth. Now, when the sun and the moon, which have gravity, all objects with mass, any mass has gravitational attraction to any other mass. It's a fundamental physical constant, so to speak. The moon has enough mass that it can exert a force on water. The sun does as well. Different kinds of tides. Usually when the moon and the sun are aligned, that is, the sun is over here and the moon is right here, they're in an alignment, they actually pull, they have enough gravitational pull to pull more water, the tidal bulge, toward them to a larger degree than they would if they were at right angles. You can see this bulge here on this side of the Earth would be a high tide zone over here, and over here in this section is kind of a lower tide. Now, a neap tide, in contrast to a spring tide over here, a neap tide is when the sun and the moon are not in alignment. So in this case, the sun is still to the right, the moon is away from the sun in some regard, and the tidal bulge is dominated again by the moon, but the sun still has some of that force pulling on this section. So basically over here in the spring tide, the high tide is high and the low tide is low. Over here in a neap tide, the high tide is high, but not as high as the spring tide high tide. The high tide is high, but the low tide isn't as low as it would be in the spring tide. So it's basically when you add the gravitational force of the sun and the moon together, you get especially high and especially low tides. When the gravitational forces are offset or not in alignment, the daily tidal range is lower. Tidal patterns vary in space and time. Sometimes you can get quite different. And anybody who is used to looking at tide tables, especially fishermen and sailors, know this, that tides don't happen exactly the same every day. But they are predictable, and they're predictable based on relationships between the sun and the moon and the point on the Earth in which those astronomical bodies are aligned. So there are several different tidal patterns. This most simple tidal pattern is the diurnal tidal pattern, and that's where there's one high tide and one low tide in a 24-hour period. This graph here shows 0, 12, 24, 12, 24. So 2 days of time. This is the start point. This is the next day at exactly that time. And this is the day after that at exactly the same time. This is 2 days of time on this graph. And this shows a low level, a high level, back to a low level. Then the next day back to a high level, and then back to the low tide. So this is a case where there are two highs and two lows in 2 days, or one high and one low in 1 day. That's called a diurnal pattern, and that's a really simple tidal pattern. They don't happen in a lot of places around the globe, but they do happen in the Gulf of Mexico, typically in the Mexican side of the Gulf. A semi-diurnal tidal pattern, on the other hand, has, in the space of one 24-hour period, has 2 highs, 1, 2 highs, and 2 lows, 1, 2. 2 lows in that 24-hour period. The way they've drawn this graph makes it a little bit confusing because it looks like there's a third here, but what we really need to think about is that this is the first one, first high, second low, second high. And then we start the second day in first low, first high, second low, second high. But what you'll notice about the semi-diurnal pattern is that the highs are relatively pretty much at the same height. They're not exactly the same height, but they're pretty close. A couple, tenths of an inch or a couple inches at most. And the lows are pretty much at the same level. That's what a semi-diurnal tidal pattern is. Now the third tidal pattern, which is actually the most common pattern, is what's called a mixed tide pattern. There are 2 highs and 2 lows each 24-hour period, but there's a large difference in the height of the highs and a large difference in the height of the lows. So in this example we have a high tide number 1, low tide number 1. Then high tide number 2 is at a different level. It's almost 6 inches Well, 4 or 5 inches less than the high tide. And then the second low, look at how much higher that second low is relative to the first. This is what's called a mixed tidal pattern. And that's actually what dominates in the western Pacific, or sorry, the Pacific Ocean, especially on the west coast of the United States, as well as actually on the west coast of the Florida shoreline. Tidal currents have the ability to do erosional and depositional work. I showed you that picture of the Baymouth Bar a few slides back, and tides actually have that ability. This is an example of what's called a tidal delta and tidal flats. The tide actually has forced its way through a barrier island and created a zone of deposition, and in the delta as well as in the back area of the flats. So that's the end of chapter 15. We'll be moving on next to Unit 6, which is Earth's dynamic atmosphere. It's a 5-chapter module. It's a big one. So get your quiz done for Unit 5. Email me with questions as always, and we'll see you back again for the lecture for chapter 16.